Hello. Now we are going to look at how to find the areas of triangles if we're given the coordinates of their corners or their vertices. As we're going through this though, it's important to remember that we know lots about the area of triangles already. So one of the formulas we know is the area of a triangle is equal to half of the base, one of the sides, times the perpendicular height away from that side. So if we go perpendicularly away from one of our sides to the far corner, that's our perpendicular height. So we already know that, and we may know other tools about finding the area of triangles. They're all still true, they're all still relevant. We're going to focus now on a new formula, but what we know about the areas of triangles is still useful, and we should keep it in mind. Now, if we have a look at this formula that we're going to focus on today, we have the area of our triangle is equal to a half times we have our big vertical lines around here. We're going to come back to them in a moment, but then we have x1, y2 minus x2, y1. Now, the vertical lines here just mean that we're always going to take the positive value of whatever comes out of this sum. So we could get a negative value out of x1 times y2 minus x2 times y1. But we're looking for an area. We're looking for a physical object, the size of something. So it wouldn't make sense to have a negative number. So these lines mean the absolute value or the size of something. We've used the same type of symbol for saying the distance between two things or the size of the distance between two things. So this just means we always take the positive value. But what might jump out at us about this formula is I only have an x1, y1 and an x2, y2. I only have 2 points, and I know that there would be 3 points for the 3 corners of a triangle. So one of the key things about this formula is that one of the corners, one of the vertices, has to sit at 0, 0. It has to sit at the origin. This formula only works if we have one of our corners sitting at 0, 0. And we can remember that by the fact that we only have 2 points of our 3 points for our triangle referred to in the formula. So let's get into using our formula. We have the area of the triangle ABC. So my first job is to write down the coordinates of A, B, and C. So that's going to be A is at in the door minus 2, down the stairs minus 4. B is going to be at in the door minus 4, down the stairs minus 3. And C is just at the origin. So this one's a nice one. We already have this criteria met. We already have one of our corners sitting at 0, 0. So I can just immediately write down this formula and sub into it with everything in brackets as always. So this is quite a complicated formula. So as with all of our formulas, we always go to our log tables and read it directly from the log tables, write it down on our page, and then write down our points directly next to it and label our points, in this case x1, y1, x2, y2. It doesn't matter which one of these is the first point. I could have called B x1, y1 and A x2, y2. All that matters is one of our corners has to be at 0, 0. We've written down our formula from our log tables, so now we're going to sub everything in. So the area is going to be equal to half, and everything in brackets, minus 2 for x1, and y2 is minus 3, minus 4 times minus 4, and tidy everything up. So we end up with minus by minus is plus 6, and minus, we're taking away minus 4 by minus 4, which would be plus 16. So we're taking away plus 16 would be minus 16. And now we have the area would be equal to minus 10 times a half. But we know this is an area, it's a physical size of something. We know taking a negative wouldn't make any sense. So what we do instead, that's what our big lines here are for. They say, I'm going to take the size of this. I'm just going to say, I take that as being 10 square units. So it's going to be, the area is just going to be half of 10. Because the other alternative, the minus 10, doesn't make any physical sense for an area. So half of 10 is just 5, so our area is just going to be 5. And we can write down units squared because we know that we're talking about the size of something. That's our area for our blue triangle. Now the other triangle that we have here is, what is the area of the triangle DEF? And if I go to my triangle DEF, I can write the coordinates of it up here just to begin with. I know D is at in the door 3, up the stairs 4. In the door 3, up the stairs 4. E is at in the door 5, up the stairs 7. And F is at in the door 5, up the stairs 4. And what might jump out at me when I'm looking at these coordinates, so I might not be given a picture, but what might jump out at me is D and F are at the same height. They're both at y is 4. I can see that in my diagram. It's a horizontal line going across from D to F, straight across my grid. And E and F have the same x coordinate, so they're directly above each other, above and below each other. So that means that I have a horizontal line between D and F, and E and F is a vertical line. Well, that means that there's a right angle in the bottom of that, in the bottom corner there of my triangle. So I have a right angle triangle. Well, finding the area of a right angle triangle is very easy. I don't need to do anything complicated. All I have to do is say, I'd find the length of my base, which is 2 units. Each one of our boxes in this case, this is not always true, but we can see in this case, each one of our boxes is 1 unit. So D to F would be 2 units, and E to F is 1, 2, 3 units. So then I can just say, well, from this base of 2, the perpendicular height, the right angled height out to the far corner is just 3 units. So I can say the area I'm looking for, the area of DEF, would just be half of the base times the perpendicular height. So that's going to be a half of 2 for the base, and perpendicularly at right angles away from that base up to the far corner is 3. So I just end up with a half of 6, which is 3. So the area of the triangle DEF is just 3 units squared for our area. So if we see that in our work, then we can just use that tool. This is still the area of a triangle we're talking about. So if we can see that another formula works, particularly a simple one like this, we're entitled to just use it because it's still true. However, we're practicing using this formula, so we're going to use this as an example, and now we know what the answer ought to be, so we're going to go and see if we get the same answer here. So doing this question, finding the area of DEF using our formula, well, we need to write down our formula, so I'm going to say the area is going to be equal to half of x1 y2. From our log tables, we write this down directly, so we put the log tables next to us and we write it down. The numbers and the letters go all over the place in this formula, so it's very easy to get muddled. And I look at that and I say, well, I have 3 points and I only have an x1, y1, x2, y2. I only have 2 points in my formula. And that reminds me, my third corner needs to go to the origin, needs to go to 0, 0. So the fact there's only 2 points there reminds me of that fact. So I'm going to send D, the point D, to 0, 0. And I'm going to do what's called a translation for that. I'm just going to move it by a particular amount in the x direction and the y direction. So I want to move the point D to where it ends up, or what we say, the image of D ends up at 0, 0. That's the location I need D to end up in. So what would I need to move it by to end up at 0, 0? Well, I'd need to take away 3 from my x value, and I'd need to take away 4 from my y value. If I take 3 away from 3, I end up at 0 for my x coordinate, and 4 away from 4, I'd end up at 0 for my y coordinate. So now D is where I need it to be. It's in the corner. It's in the origin, I should say. We can look at that visually as well on our diagram. I need to take this corner here, D, and I need to move it to 0, 0. So I'd need to move it to the left. I'd need to make X 3 units smaller, and I'd need to bring it down 4 steps. I'd need to bring Y down by 4. And that's what I've written in here. Well, to keep the triangle the same shape, so if I just moved D, I'd obviously change the shape of the triangle. So I need to move E and F by the same amount in the same direction, and then I'll have just moved the position of the triangle without changing its shape. So I'm going to subtract 3 from my X, 3 from my Y, 4 from my Y, 3 from my X, 4 from my Y, and find out where E and F end up. So the image of E, the new location for E, is going to be at 2, 3. So 5 minus 3 is 2, 7 minus 4 is 3. And the new location of F, the image of F, we say is at 5 minus 3 is 2, and 4 minus 4 is 0. So I'm going to draw in that translation on our diagram to see what we mean by it. When I have drawn in my translation, so I've moved all of my corners by the same amount in the same direction, so D is now down at the origin, E ends up at 2, 3, and F's image ends up at 2, 0. I can see that the green triangle here is the same size and shape as the original red triangle. All I've done is move it down all of the corners by the same amount in the same direction. The base of this triangle is still 2 units long, and the height away from that base, the perpendicular height away from that base, is still 3. So it's the same shape, we've just been able to move everything along to where we need it to use our formula. So now we can call E our x1 and our y1, and F's image our x2 and our y2. So we're using the image of E and the image of F because it's the same shape of triangle. We'll get the same area as we would have from our original red triangle. But now we can use this formula because we have a corner at 0, 0. The area is half of, sub everything in brackets, x1 is 2 on y2 is 0, minus x2 is 2, and y1 is 3. So we know where we should end up. We should end up with 3 square units, and we'll see if we do in a moment. We end up with half of 2 by 0 is just 0, and minus 6, 0, oops, and that's a modulus symbol, an absolute value symbol. So the area is equal to a half of the absolute value of minus 6. Well, again, this is a physical area. It doesn't make any sense to take a negative number, so we have this to remind us of that. We're just going to take the positive version of that, so we end up with half of 6 is going to be 3. So the area is just going to be 3 units squared, which we can see is what we got when we did our half the base times the perpendicular height version of our work. So we can see how we can use this formula so long as one of our corners is at the origin, moved to 0, 0, or starts at 0, 0. Once one of our corners is at 0, 0, we can use the other 2 points to get the area of our triangle. And that is what we need for now.